Welcome to Dunwoody College of Technology. This is Mechanical Engineering 3250 heat transfer. We'll be working through an example from Chapter 3. So let's take a look at what we've got going on here. So here's our problem. We're told we have a commercial grade freezer, so we have some information about that. We're going to look at what this wall looks like. So we have an exterior sheet of carbon steel on the outside. On the inside, we have a same thickness aluminum alloy, and sandwiched between them we have a layer of cork insulation. We also have some adhesive that's holding this whole sandwich together, and we know something about the contact resistance. So if we look here, we're listed what the contact resistance is for those interfaces between the insulation and those material surfaces, and we're asked for what is the steady state cooling load that we need to have throughout the time to maintain temperatures of 22°C outside and -6°C inside. So as we look at this problem, we are looking for what the composite wall temperature difference is throughout the whole thing. And we don't necessarily need what the intermediate temperatures are, so I'm going to use a thermal resistance approach as we look at this assembly, and we'll go from there. So let's jump in. We'll follow the problem-solving approach laid out in the Bergman book, and we'll go from there. So I'm going to switch over just to the screen so I have enough room to write, and we'll hopefully get to the end of this together. Alright, so we've got our commercial freezer. So we need to start with our known. What do we know about this system? Well, we know it's a commercial freezer, 3 meter, cubicle freezer of known construction. So by that I mean materials. I also mean that we know the thicknesses and contact resistances. Alright, what are we looking for? Our find here. We're looking for cooling load for steady state. What does that really mean? That's our heat loss. Right? How much heat are we removing from the system to keep it at the temperatures that we're specifying? So now we'll move on to our schematic. So I've got a cubic freezer. That's not a very good cube, but you get the idea. So we have 3 meters on each side. And if we look at a cross section of this thing, I'm going to draw it oversized. So inside, what do we have? We have -6°C. We have some aluminum here, cork, and then carbon steel. On the outside, we're at 22°C. So as we look at that, we have this system going on. We also have some contact resistance in here. And remember, those are based on the flux, not on the heat rate. So that's why I've got the double prime on those. So if I'm drawing a thermal circuit for this guy, we're going to have, and we know this is the surface temperature there, is that value. It's not the air temperature. And actually in this case I think we're assuming that the air temperature and the surface temperature are the same. We don't know anything about convection at this point. So we have a thermal resistance for the aluminum, thermal resistance for the contact, thermal resistance for the cork, thermal resistance for the other contact, and then thermal resistance for the carbon steel, and away we go. Our TC, our cork, our TC, and we have our aluminum. Alright, so there's our assembly. Let's talk about that just for a minute. So as we're looking at this system, what do we have going on? Which way is heat going to be moving in this system? Right to left or left to right? I gave you the answer there. We've got the hotter temperature over here on the outside, so our heat flow is going to be moving right to left. And I'm going to do this on the area balance basis, so I'm going to look for the flux. So it's going to be something watts per meter squared. And what I'm finally looking for is the cooling load, which we've got up here. That's going to be something like Qx. So what do we have for that? Well, we're going to take our Qx double prime multiplied by our area, which we get from this guy here. It's going to be 6 sides times 3 meters by 3 meters. We'll get 54 meters squared. So that's kind of the goal that we're going for. So we're going to use the thermal circuit that we have over here and use that to base our calculations on, and then we'll go back and multiply by that area at the end. So without further ado, let's get in there. So what do we have going on here? So we've got, don't I get more area? I guess not. Let's get a little bit more space. All right, so now our analysis section, our properties, sorry, assumptions and properties. So our assumptions, we were told some of them. So assumption 1 is steady state. So our temperature is not changing over time. Another assumption we might want to make is one-dimensional conduction. Now at the edges we might actually have a couple pathways for heat to flow, but we're in the section on one-dimensional conduction. We'll find that at that edge, at that weird interface, we'll actually have more resistance than we do if we assume it's all one 54 meter squared sheet, if you will. And third, we're going to assume constant properties. That allows us to pull that K of T out, and so we can So let's kind of guess an average temperature and evaluate our properties at those conditions. So let's give us a little more than I was bargaining for. So our properties, we're going to look up where we're getting these from. So we're going to have aluminum. I'm going to say that's at 267. If I look in the book, I'm going to table A1 for properties of 2024. If I look there, I have at 200 K, our conductivity is 163. At 300 K is 177. So interpolating between those at 267, I'm going to say K is 173 watts per meter Kelvin. We also have carbon steel. I believe we'll use AISI 1010. I don't think they told us that in the book, but we're at 22 C on the outside there, so we add that to 273, so we're going to be at 295 Kelvin. Again, that's in table A1. We're using AISI 1010. So if I look there, I find that at 300 Kelvin, K equals 63.9 watt per meter Kelvin. There's no lower values. So at that point, I might say, okay, well, I see that from the higher values that things are decreasing as I increase temperature. So maybe I'd guess something 64, 64.2, I don't know. Or I can say, to be conservative, I'm going to go with this number, because that will get me a little lower resistance. I guess that would be about be going the other way, but it's very minor at that point. All right, and then last we need cork insulation. For this one, we need to go to another table. This is in table A3 on insulated materials, and so we have cork at 300 Kelvin. K is 0.039 watt per meter Kelvin. So there you have it. So we've got our properties. We don't really need anything else. We only need K. So we'll give ourselves a little bit more room here. Jump into the analysis part. So what I'm looking for at the end game here is our heat rate. I'm going to say that's Qx double prime, our flux, times our area. Qx double prime is the name of the game here. How am I going to find that? Well, I might recall kind of the thermal Ohm's law is Qx RT, and if I write that in the flux form, it's still this. I just have Qx double prime RT double prime, and I'm going to use this because that's what my contact resistances are based on. I could multiply everything up above, but we'll go with this guy here. So our delta T is 22 degrees C minus negative 6 degrees C, 28 degrees C, or 28 Kelvin. It's a temperature difference, so I don't need to really do any of that 273 business. And now we need to find our thermal resistances. So RT C for the aluminum, it's going to be our length of our aluminum over K of aluminum, 0.00635 meters. And our conductivity again was up here. What do we got? 173 watts per meter Kelvin. And actually, I'm gonna go to the. I'll just make this a total. So I'm going to add in now that contact resistance, 2.5 times 10 to the negative 4. We get watts per meter squared Kelvin for that, plus the resistance of our cork, which was 0.1 meters over 0.039 watts per meter Kelvin, plus another thermal resistance from the contact, and then our steel, 0.0635 meters over, what were we with that, 63.9 watts per meter Kelvin. So if we look at that, what are our bigger terms? Well, these guys are pretty small. This one's going to be smaller than our steel, right? We have the same thickness. This one's about 3 times the conductivity, so our resistance is going to be a little lower as a result, but both pretty small because of our thickness there. And our biggest resistance here is going to be probably this cork that's going on here. So I've got the biggest thickness, the smallest conductivity, and we'll find out whether or not that's bigger than this guy. I think it will be, right? So I'm already at 0.1. This is 0.00025. So, and I'm dividing by something less than 1. So that's going to be my biggest driver here. So let's take a look what else we can find out here. So if I add those all up, RT, I'll just call it RT total, double prime. So plug those into a calculator. What do I find? I find my total. I'm going to write it out as numbers here for a minute. 0.0003670.5 for my aluminum, plus 2 times that 2.5 times 10 to the negative 4 for the 2 contacts, plus 2.564 for my cork, plus my steel is 0.0009937.4. So this is my carbon steel, this is my cork, contacts, this is my aluminum. So what do we see with that? Well, by far my cork is my biggest resistance. If I add those all together, I find that my total contact resistance there is my total resistance, excuse me, 2.5655 watts meters, excuse me. Yep, meters squared Kelvin per watt. And yep, so our meter squared Kelvin comes up to the top, my watt is left on the bottom. So now we go back to this equation up here. We know we're looking for Qx. So if I rearrange this guy, Qx double prime equals delta T over RT total double prime. So we have Qx double prime is 28 Kelvin over 2.5655 meters squared Kelvin per watt. So when I do that division, my kelvins are going to cancel out, my watt's going to go up to the top, I get watts per meter squared. Fantastic. So this guy becomes 10.914 watts per meter squared. And now finally, what are we looking for? Qx, double prime times the area. So I get 10.914 times 6 times 3 meters times 3 meters. Qx is, I get 589.4 watts. I want to report that out to 3 significant figures just to give a certain amount of level there. So I need to be removing about 590 watts from the freezer to maintain these temperatures. And that doesn't seem too unreasonable. Now, it doesn't ask us for this specifically, but if I go back up and look at my construction here, I might be curious to know how much of that thermal resistance is due to the cork versus the other properties. So let's take a look at that for a moment. So comments at the end here. Insulation is biggest resistance. If I neglect the other, other resistances, so if I just do the analysis here, Qx double prime equals 28, so I'm saying I've got 28 Kelvin across the cork itself for 2.564 meters squared Kelvin per watt. That number goes to 589.7 watts per meter squared. So comparing that with that's times the 54 already, so let me add that in there. Add that in my notes, times 54 meters squared. So I get Qx is 589.7. So including those other resistances, reduces Qx by 0.05%. So I could have just neglected them off the bat, called it just fine, don't worry about the contact resistance, don't worry about the aluminum and the steel, and we would be there. So I hope this was a helpful video for you. I hope we can able to help this 1D conduction, particularly composite walls. So we had the contact resistances, we had the 3 different materials, so we looked up some material properties, we formulated Ohm's law for thermal circuits, we drew that thermal circuit, so we had a nice series circuit, and I hope that was beneficial to you in your homework studies. So we'll see you in class or around. Thank you so much for watching.